Hello there, and welcome to Sleepy Science Vault. There is a light in the sky that cannot be planned, cannot be predicted with certainty, and cannot ever be seen the same way twice. It moves. It breathes. It shifts across the darkness in waves and ribbons of color, as though the night itself has come alive with something vast and unhurried. People travel thousands of miles just for the chance of seeing it, and even then, it offers no guarantees. It simply appears, on its own terms, in its own time. This is the Aurora Borealis. And it is one of the most extraordinary things our planet has ever made. At its most basic, an aurora is what happens when charged particles streaming from the sun collide with gases high up in Earth's atmosphere. But to call it that, to reduce it to a collision, is a little like describing music as air pressure. Technically accurate, and entirely insufficient. Because what those collisions produce is something that has stopped human beings in their tracks for as long as we have been looking up at the sky. Curtains of light, folding and unfolding across the heavens. Beams that sweep sideways in seconds. Soft glowing arcs that hang above the horizon like the edge of another world pressing gently through. No two auroral displays are ever identical. Not one. In all of recorded history, in all the nights that people have stood in the cold and looked upward, the aurora has never repeated itself exactly. Every appearance is its own thing, its own shape, its own color, its own particular mood. There is something quietly extraordinary about that. The sky, endlessly inventive. The aurora takes many forms. Sometimes it appears as a simple arc, a smooth, luminous curve low on the horizon, almost like a distant city's glow, but softer and stranger. Other times it rises into tall vertical rays, like columns of light standing between the earth and the stars. And then there are the moments, the rare, breathtaking moments, when it breaks into what scientists call a corona, rays spreading outward from a single point directly overhead, as though you are standing at the center of something enormous looking straight up into it. The movement of the aurora is one of the things that makes it so difficult to describe to someone who has never seen it. It doesn't just sit there. It dances. Not quickly, not frantically, but with a kind of fluid, purposeful grace. Beams shift and ripple. Folds in the light open and close. Brightness pulses through a curtain from one end to the other, like a slow wave moving through fabric hung in a gentle wind. What creates these patterns is the shape of Earth's magnetic field. The aurora doesn't appear randomly across the sky, it follows invisible lines, the same lines that make a compass needle point north. Charged particles from the sun are guided by these field lines down toward the poles, and as the magnetic field shifts and responds to the solar wind, the aurora responds with it. The patterns you see, the curves, the rays, the sudden brightening, are the magnetic field made visible. You are watching physics, written in light, across the entire sky. And the curtain effect, that particular quality that makes the aurora look like something soft and flowing suspended high above you, comes from these same field lines. The particles stream downward in long threads, and the glow they produce traces those threads, creating the appearance of vast hanging drapery, slowly turning in a wind that isn't wind at all, but something far more ancient and invisible. The name itself carries a kind of poetry. Aurora Borealis. In Latin, aurora means dawn, the first light of morning, the soft glow that appears before the sun has fully risen. And Borealis comes from Boreas, the Greek god of the north wind. So the name, taken together, means something like the dawn of the north wind. The Northern Dawn. It is a beautiful name, and it was given by a man who saw the lights one night in January, in the year 1621, and felt, as so many people have felt since, that what he was looking at needed a name worthy of it. That man was Pierre Gassendi, a French philosopher, mathematician, and scientist. He had been watching the aurora dance across the sky when he wrote down what he saw and chose the words that would stay with it forever. Aurora Borealis. He borrowed from Roman mythology and Greek legend, and in doing so, he gave one of nature's most elusive spectacles a name that sounds, even now, like something that belongs to it completely. Before Gassendi's name took hold, the lights had been called many things: fire in the sky, spirits walking, the breath of the gods. Different cultures had looked at the same phenomenon and reached for entirely different explanations, each one reflecting something about what they valued, what they feared, what they hoped the universe might be. But the name Aurora Borealis, that name endured. It spread across languages and centuries, and today, when someone stands in the cold dark of a Finnish forest or on the frozen tundra of northern Canada and looks up to see those curtains of green and violet unfolding above them, they are still reaching for the same word a French philosopher reached for 400 years ago. There is something deeply human in that. The need to name the beautiful things. To hold them still, just for a moment, with language, even as the lights themselves keep moving. There is some debate, quietly held among historians of science, about who truly deserves credit for naming the Aurora Borealis. Pierre Gassendi is most often cited, and with good reason. But some accounts suggest that Galileo Galilei may have been involved as well, either in coining the name or in using it around the same period. The historical record here is a little blurred, as it often is when two brilliant minds are working through the same era, looking at the same sky. What is certain is that the name emerged from that moment in the early 17th century when European science was beginning to reach for language precise enough to describe the natural world. Whether Gassendi named it, or Galileo, or whether they arrived at it together in some way, what they gave us was a phrase that has outlasted almost everything else from their time. And yet, long before either of them ever wrote it down, people were already calling these lights by another name. The Northern Lights. It sounds almost too simple for something so spectacular. But that name, or versions of it, stretches back through centuries of language and tradition across the northern world. Norse peoples spoke of them. Scots recorded sightings in their chronicles. Across Scandinavia and Iceland, the lights were a familiar presence in the winter sky, close enough to everyday life that they needed an everyday name. Northern Lights. The lights of the North. Plain, honest, and in its own way, just as enduring as the Latin. The earliest written observations we can reliably point to go back to 1619. That year, accounts were committed to paper, careful, wondering descriptions of what had appeared in the sky. But the seeing of the aurora is far, far older than any written record. It goes back to a time before writing, before cities, before any of the frameworks we use to organize knowledge. It goes back to the first people who looked up and tried to understand what they were witnessing with the only tools they had: story and imagination, and the deep human instinct to make meaning from mystery. The myths and explanations that ancient cultures built around the aurora are among the most beautiful things in the history of human thought. Some traditions held that the lights were the spirits of the dead, traveling across the sky on their way to whatever lay beyond. In parts of medieval Europe, a reddish aurora, rare but not unheard of at lower latitudes, was sometimes interpreted as a terrible omen. Blood in the sky. War coming. There are historians who believe certain accounts of the aurora influenced the imagery of the apocalypse in early Christian writings. So strange and overwhelming was the sight of the lights to people who had never seen them before and had no science to explain them. The Inuit peoples of the Arctic had a remarkably vivid way of imagining the northern lights. In one tradition, the lights were said to be the spirits of the dead playing a game, and the game they played was football, but played with a walrus skull. Picture that image for a moment. Not fire, not gods, not cosmic force, but the dead, at play, joyful in whatever existence came after this one, kicking a walrus skull across the heavens and leaving trails of light behind them. There is something in that image that is not frightening at all. It is almost warm. To whistle at the aurora, in some Inuit communities, was believed to call the lights closer. To wave at them was to invite them to approach. The lights were not remote or unknowable. They were neighbors of a kind, residents of the same world, just living above it. In Finland, the aurora had a different name and a different story. The Finnish word for the northern lights is revanchelit, which translates, literally, as fox fires. The legend behind it tells of a great Arctic fox, running across the fells in the far north, its tail sweeping across the snow and sending sparks flying upward into the sky. As the fox ran faster, the sparks rose higher, scattering into color and light across the dark heavens. The fox kept running. The lights kept moving. And what you were seeing, when you looked up, was the trail of something swift and wild and alive, passing just overhead. It is a beautiful piece of storytelling. And when you consider that the aurora does move like something alive, fluid, quick, unpredictable, you can see why a fox felt like the right image. Something that cannot be caught. Something always just ahead of you. But the fox is not the origin of the aurora. The actual origin is something far larger, far stranger, and far more difficult for the human mind to fully hold. It begins, as so many things on this planet begin, with the sun. The sun is not simply the star that lights our days. It is an active, dynamic, restless thing, a churning body of plasma and magnetic fields that sends material outward into space in a constant, invisible stream. This is the solar wind. A flow of charged particles, mostly electrons and protons, radiating outward from the sun in every direction, filling the space between planets, pressing outward past Mars, past Jupiter, past the farthest edges of the solar system. The Earth passes through this wind every second of every day. The scale of what we are talking about when we talk about space weather is genuinely difficult to absorb. The sun is about 150 million kilometers from Earth. The solar wind travels at somewhere between 400 and 800 kilometers per second. Events on the sun's surface can send disturbances across that entire distance and reach Earth within a matter of days, or, in extreme cases, hours. We live, all of us, inside the sun's extended atmosphere. The aurora is simply the place where we can see that atmosphere touching ours. And sometimes, the sun does more than simply breathe. Sometimes it erupts. Solar flares are intense bursts of radiation released from the sun's surface, often from regions where the magnetic field has become tangled and stressed. They release energy equivalent to millions of nuclear explosions, in a flash that can last minutes or hours. The radiation from a solar flare reaches Earth in about 8 minutes, traveling at the speed of light, but the charged particles follow behind more slowly, arriving over the next day or two. Then there are coronal mass ejections, CMEs, as scientists call them. These are something different and even more dramatic. A coronal mass ejection is a vast cloud of magnetized plasma, billions of tons of it, hurled outward from the sun in a single explosive event. When a large CME is aimed in Earth's direction and makes contact with our magnetic field, the result is a geomagnetic storm. The magnetic field shudders and reshapes. The aurora intensifies dramatically. And sometimes, on the most powerful occasions, it becomes visible far beyond the Arctic, appearing over cities and countries that rarely or never see it. People in France, in Spain, in the southern United States, have stepped outside on certain rare nights and found the sky alive with color. The aurora, at those moments, is no longer a thing of the far north. It is a planetary event. A reminder that we are not sealed off from the rest of the solar system, that we are embedded in it, subject to it, lit up by it. The fox is still running. Only now we know what it is made of. And somehow, knowing makes it no less extraordinary. The sun does not simply shine. It exhales. At any given moment, the surface of the sun is alive with motion, with loops of magnetic energy rising and falling, with regions of intense heat and pressure building until they can no longer be contained. And from these regions, the sun releases material into space in ways that range from the subtle to the almost incomprehensibly powerful. The solar wind itself is constant. It never stops. Day and night, across every season, the sun is shedding a stream of electrically charged particles outward in all directions, a ceaseless breath that fills the entire inner solar system. These particles, mostly electrons and protons stripped from hydrogen atoms, travel outward at extraordinary speeds, invisible and silent, passing through the void between worlds without any friction to slow them down. By the time they reach Earth, they have been traveling for days. They carry with them information about conditions on the sun, magnetic signatures, energy levels, the particular mood of our star on the day they were released. But the solar wind, steady as it is only one part of the story. The more dramatic events, the ones that produce the most spectacular auroral displays, the ones that have been known to affect satellites and power grids and radio communications across entire continents, are the coronal mass ejections. A coronal mass ejection is not simply a puff of particles. It is a catastrophic release. When the sun's magnetic field lines become sufficiently stressed, twisted and compressed by the constant churning of solar plasma, they can suddenly snap into a new configuration, releasing an enormous burst of energy in the process. And riding that burst, like a wave on a vast invisible ocean, comes a cloud of magnetized plasma. Billions upon billions of tons of it. A structure larger than the Earth itself, sometimes larger than several Earths, moving outward through space at speeds that can reach thousands of kilometers per second. When a coronal mass ejection is pointed away from Earth, we hardly notice it at all. It moves off into deep space, and whatever worlds lie in its path, if any, feel its effects instead. But when a CME is launched in our direction, something very different happens. The cloud travels. It expands as it goes, a bubble of magnetized material growing larger as it pushes outward through the solar wind. For a day, sometimes 2, sometimes 3, it crosses the distance between the Sun and Earth. Spacecraft positioned between the Sun and our planet can detect its approach, can measure its speed, its magnetic orientation, its likely impact. And then it arrives. When a large coronal mass ejection strikes Earth's magnetic field, the interaction it produces is one of the most energetic events our planet regularly experiences. The magnetic field is compressed on the side facing the Sun, pushed inward by the sheer force of the incoming material. On the opposite side, it stretches outward, pulled into a long tail. Currents of energy flow through the magnetosphere, the region of space governed by Earth's magnetic influence, and particles are funneled down toward the polar regions with far greater intensity than the ordinary solar wind produces. The result is an aurora unlike the kind seen on quiet nights. Brighter, more dynamic, spread across a wider band of latitude. Colors that might normally be faint become vivid. Shapes that would normally be slow become rapid and dramatic. On the most powerful occasions, the aurora can be seen from places that almost never experience it, from Central Europe, from the southern United States, from latitudes where generations of people have lived without ever once seeing the sky do this. The geomagnetic storm that produces these events can last for hours, or for days, pulsing and ebbing as the magnetosphere absorbs and responds to the incoming energy. Scientists rate these storms on a scale, the most extreme being the kind of event that occurs perhaps once in a generation. The most powerful geomagnetic storm in recorded history struck in September of 1859, and it was so intense that telegraph systems across North America and Europe failed entirely, with some operators reporting that their equipment sparked and caught fire even when disconnected from their power sources. The aurora was seen as far south as Cuba, as far south as Hawaii. People who had never seen anything like it in their lives woke in the night thinking the sky was on fire. We have not seen an event of that magnitude since. But we know it is possible. And we watch the sun carefully for signs that something like it might be building. Alongside the coronal mass ejections, there is another, quieter source of enhanced solar activity, one that operates not through explosive eruption but through steady, persistent outflow. These are coronal holes. The sun's corona, its outermost atmosphere, is normally held in place by the magnetic field, which loops and arches above the surface, trapping material within its structures. But in some regions, the magnetic field lines open outward rather than looping back. In these regions, there is nothing to hold the solar wind in. It simply streams outward, freely and rapidly, like water from an open pipe rather than a contained one. The solar wind that pours from coronal holes is faster than ordinary solar wind. Significantly faster. And when this fast-moving stream rotates into alignment with Earth, which happens regularly as the sun slowly turns, it strikes the magnetosphere with more force than the background wind, producing what scientists call a high-speed stream event. These are gentler than coronal mass ejections, but they can last longer, and they produce their own enhancements in auroral activity. Quiet nights of steady, beautiful displays, rather than the overwhelming brightness of a full geomagnetic storm. The sun itself moves through cycles that govern how active all of this is. Every 11 years, approximately, the sun completes one solar cycle. It moves from a period of relative calm, solar minimum, through a period of increasing activity, solar maximum, and back again. At solar minimum, the sun's surface is relatively quiet. Sunspots are rare. Coronal mass ejections are infrequent. The aurora is still there, still visible from high latitudes on clear nights, but it is less intense, less dramatic, less likely to spread beyond the polar regions. At solar maximum, everything changes. Sunspots multiply. The sun's magnetic field becomes more tangled and complex, and with that complexity comes greater instability. Flares occur more frequently. Coronal mass ejections become more numerous and more powerful. The aurora intensifies, and the band of latitude within which it can be seen widens. Solar maximum is the season of the aurora, the time when the lights are most reliably spectacular, most likely to appear on a given night, most likely to move beyond their usual home in the Arctic and Antarctic and grace the skies of the wider world. We also now have ways of anticipating when the aurora might be active, warnings, of a kind, that give skywatchers notice that something interesting may be coming. Satellites positioned at a point between Earth and the Sun called the L1 Lagrange point sit in a kind of gravitational balance, neither falling toward Earth nor drifting back toward the Sun. From this vantage point, they can detect the arrival of a coronal mass ejection before it reaches us. They measure the speed and density of the incoming material. They measure something called the BZ component of the magnetic field, a measure of whether the incoming solar magnetic field is pointing northward or southward. This matters enormously, as we will come to understand, because it determines how effectively the solar material will interact with Earth's own field. The warning time these satellites provide is not generous, typically somewhere between 15 minutes and an hour. But it is enough for scientists to alert operators of power grids and satellite systems. It is enough for aurora chasers to know that tonight, the sky may be doing something worth watching. Now consider the journey those particles have made. They began at the surface of the sun, released in a moment of magnetic energy that no human eye will ever see directly, a flash of radiation, a burst of plasma, a cloud of charged material hurled outward into the dark. For anywhere from 1 to 3 days, depending on its speed, this material crosses space. Not empty space, exactly. The solar wind fills the space between planets with a thin but real medium, and it is through this medium that the ejected material travels, pushing ahead of it like a bow wave. The magnetic field plays a critical role in how this material moves. Plasma, which is what the solar wind fundamentally is, cannot easily cross magnetic field lines. Instead, it tends to travel along them, guided by their geometry. The sun's own magnetic field extends outward into space, carried along by the solar wind, forming what scientists call the interplanetary magnetic field. This field spirals outward from the sun like the pattern on a spinning garden sprinkler, a shape known as the Parker spiral, named for the physicist Eugene Parker, who first described it mathematically in 1958 and was initially not believed. The charged particles of the solar wind are effectively roped to these magnetic field lines. They follow them outward through space, guided by invisible structure across distances that would take a human spacecraft years to cross under its own power. In a very real sense, the solar wind does not simply drift outward randomly. It flows along channels defined by magnetism, organized by forces that extend from the surface of the sun all the way to the outer edges of the solar system and beyond. Most of the solar wind that reaches Earth never makes it to the atmosphere at all. Earth has a shield. Not one made of metal or stone or any material we could touch, but one that is no less real for that. It is the magnetosphere, the region of space around our planet that is dominated by Earth's own magnetic field. And for most of the solar wind that arrives at our doorstep, this shield is entirely effective. The magnetosphere deflects the bulk of the incoming charged particles, sweeping them around the planet in much the same way that the prow of a ship divides water. The particles curve around the field, following its geometry, and most of them continue on past Earth without ever entering the atmosphere. From a distance, the interaction would look something like a stream of water flowing around a stone, with the stone being Earth, surrounded by its invisible field, and the water being the solar wind parting gracefully around it. Without this shield, the surface of the Earth would be bombarded by radiation at levels incompatible with the kind of complex life that exists here. The atmosphere would erode over geological time, stripped away particle by particle the way Mars, which lost its magnetic field long ago, has lost most of its own atmosphere over billions of years. The oceans might not exist. The conditions that allowed life to emerge and persist on this planet are, in no small part, a consequence of the fact that Earth has a powerful, active magnetic field. We live inside a magnetic cocoon. And most of the time, it holds. But not always. Not completely. There are places where the shield is thinner, where the geometry of the magnetic field creates pathways that the solar wind can, under the right conditions, find its way through, not by overwhelming the shield, but by slipping along its edges, through gaps and channels that open and close as the field responds to the incoming material. These pathways lead, ultimately, to the polar regions. And what happens when the solar wind finds its way through them is what we have been building toward all along. The aurora is not a failure of the shield. It is what happens at the boundary where the shield and the solar wind meet, where energy is exchanged, where particles are redirected, where the invisible architecture of Earth's magnetic field becomes, for a few hours on a dark winter night, something you can look up and see with your own eyes. It is the most beautiful scene in the universe. And it runs around the top and bottom of the world, waiting for the right conditions to make itself known. Earth is not uniformly magnetic. The field that surrounds our planet, that great invisible structure stretching out into space, is not equal in all directions, not consistent at every point on the globe. It has a shape. It has regions of greater and lesser strength, regions where the lines of force converge and concentrate, and regions where they spread more loosely. In the places where the magnetic field is most concentrated, most intense, most tightly wound, are the poles. At the poles, the magnetic field lines don't run parallel to the surface the way they do near the equator. They plunge downward, diving toward the Earth at steep angles, like the threads of a funnel narrowing toward a single point. It is this geometry, this plunging, converging structure, that makes the polar regions the natural destination for the charged particles carried by the solar wind. The particles don't simply wander there by chance. They are guided there, directed there by the same forces that have governed the movement of charged matter since the earliest moments of the universe. When a charged particle, an electron, say, moving at tremendous speed through space, enters a region where a magnetic field is growing stronger, something interesting happens. The particle begins to spiral. It wraps itself around the field line, corkscrewing along it, moving in a tight helix that carries it forward while simultaneously spinning it around the line's axis. And as the field grows stronger, as the lines converge more tightly toward the pole, the spiral tightens. The particle slows along its forward path, compresses, and in many cases is reflected back, bounced away as though by an invisible wall, sent spiraling back in the direction it came from. This is what physicists call magnetic mirroring. And it means that Earth's magnetic field does not simply deflect particles at its outer boundary, it actively traps them. Vast populations of electrons and protons become caught between the two poles, bouncing back and forth along field lines, spiraling north and then reflected south and then reflected north again, sometimes for seconds, sometimes for hours, sometimes for days. These populations of trapped particles form what are known as the Van Allen radiation belts, enormous donut-shaped regions encircling the Earth, filled with energetic particles that have nowhere to go and nothing to do but keep moving. But some particles do make it through. Some find pathways, particularly during geomagnetic disturbances, when the magnetosphere is compressed and reshaped by incoming solar material, where the mirroring fails, where the balance is disrupted, and the particle is no longer reflected but carried all the way down. Down along the field line. Down toward the atmosphere. Down to where the air is dense enough to matter. And it is there, at the base of those magnetic funnels, that the aurora begins. The region where auroras form is not scattered randomly across the polar skies. It follows a pattern, a ring, or more precisely an oval, encircling each magnetic pole. Scientists call this the auroral oval. It is a band, typically a few hundred kilometers wide, that sits between roughly 65 and 75 degrees of magnetic latitude, though its exact position and width shift constantly in response to solar activity. On quiet nights, when solar activity is low, the auroral oval is relatively narrow and sits close to the magnetic poles. Someone standing at 60 degrees latitude, roughly the latitude of southern Alaska or southern Scandinavia, might not see it at all, or might catch only a faint glow on the northern horizon, the edge of something happening further north. But when a geomagnetic storm arrives, when a coronal mass ejection delivers a surge of energy into the magnetosphere, the oval expands. It widens and pushes toward lower latitudes, sometimes dramatically. The band that normally hangs over the Arctic sweeps southward, and suddenly the aurora is visible not just from Finland or northern Canada, but from Scotland, from Germany, from the northern United States. On the most powerful occasions, it reaches further still. The oval exists over both poles simultaneously. There is an aurora australis, a southern lights, that mirrors the Aurora Borealis in the south, tracing its own oval around the magnetic South Pole, visible from Antarctica and, on active nights, from the southern tips of South America, from Tasmania, from the southernmost parts of New Zealand. The two auroras are not identical. They respond to the same solar input, but the magnetosphere's geometry differs slightly between the poles, but they are deeply connected. Often, when the northern aurora blazes, the southern aurora blazes in answer. Now, the magnetic poles are not the same as the geographic poles. The geographic North Pole is the axis around which the Earth rotates. The magnetic North Pole is the point toward which a compass needle points, and these 2 points are separated by a significant distance. At present, the magnetic North Pole sits in the Canadian Arctic, north of the mainland but south of the geographic pole, drifting at a rate that has been accelerating over recent decades. It has moved considerably during the last century, shifting from a position north of Canada toward one that is now moving in the direction of Siberia. This drift matters for aurora watchers. Because the auroral oval is organized around the magnetic pole, not the geographic one, the best places on Earth to see the aurora are not necessarily the geographically northernmost ones. What matters is proximity to the magnetic pole and position within the auroral oval. This is why places like Tromsø in northern Norway, Fairbanks in Alaska, Yellowknife in northern Canada, and Rovaniemi in Finnish Lapland are considered among the finest aurora watching locations on the planet. They sit, at least for now, within or very near the auroral oval on a regular basis. They are in the right place, relative not to the spinning axis of the Earth, but to its magnetic heart. And on the most active nights, the strongest aurora of all concentrates within a relatively narrow band, perhaps 30 to 40 kilometers wide in places, where the most intense particle precipitation falls. Within this band, the lights can be overwhelming. Bright enough to cast faint shadows. Bright enough to be visible even through thin cloud cover. Moving so quickly that the eye struggles to follow them. This is where the aurora is at its most alive, its most theatrical, its most impossible to look away from. But what is actually happening in those moments? What is the mechanism behind the light itself? To understand that, we need to go smaller. Much smaller. Down past the scale of planets and magnetic fields, past the scale of kilometers and clouds, all the way down to the scale of individual atoms. The atmosphere at the altitude where auroras form is not the thick, familiar air of the surface. It is extraordinarily thin, rarefied to a degree that is difficult to imagine. the density of the air at 100 kilometers above the ground is less than 1/1,000,000th of what it is at sea level. At 200 kilometers, it is thinner still. And yet, thin as it is, there is still matter there. There are still atoms, oxygen atoms, nitrogen molecules, drifting in the dark above the bulk of the atmosphere, high above any weather, high above any clouds, in a region called the thermosphere. These atoms exist in their normal, resting state. Their electrons, the tiny, negatively charged particles that orbit each atomic nucleus, are arranged in the lowest energy configurations available to them. Everything is in balance. Everything is quiet. And then a charged particle arrives. It comes screaming down the magnetic field line at tremendous speed, an electron from the solar wind, or a proton, carrying enormous kinetic energy. When it collides with one of those atmospheric atoms, something remarkable happens. The energy from the collision is transferred, partially or wholly, to one of the atom's own electrons. And that electron, suddenly flush with energy it cannot hold in its current position, jumps. It leaps to a higher energy level, a higher orbital shell, as though it has climbed a step on a ladder it wasn't standing on before. This state cannot last. It is an excited state, and excited states are inherently temporary. The electron can only hold that extra energy for a fraction of a second, sometimes much less, before it falls back down to its original level. It descends the ladder it climbed, returns to its resting position. But the energy it carried upward has to go somewhere. Energy does not simply vanish. And so when the electron falls back, it releases that borrowed energy in the only form available to it. It emits a photon, a single particle of light, with a specific energy that corresponds precisely to the distance of the electron's fall. That photon travels outward from the atom in all directions. If it happens to travel downward, toward Earth, it passes through the thin upper atmosphere without being absorbed, eventually reaching the surface where it might enter a human eye. If it travels upward, it escapes into space, where it joins the faint glow of the aurora visible from orbit. And here is where color enters the story. The energy of a photon determines its color. High-energy photons are toward the blue and violet end of the spectrum. Lower-energy photons sit toward the red end. And the energy of each photon released by an excited atom depends on exactly which atom it is, and which energy level the electron fell from into. Oxygen atoms at around 100 kilometers altitude produce, most commonly, the color that most people associate with the aurora, that vivid, electric green. It is the most efficient emission at that altitude, the one that oxygen produces most readily under the particular pressure and temperature conditions found there. The photons pour out in the green wavelength, and when millions of atoms are doing this simultaneously across a vast curtain of energized atmosphere, the result is that flowing, luminous green that has become the signature color of the northern lights. Higher up, at altitudes of 200 kilometers and above, where the atmosphere is thinner still, oxygen behaves differently. At those heights, where collisions between atoms are rarer and the excited states persist for longer before releasing their photons, oxygen produces red light instead. This red aurora is rarer, appears at higher altitudes, and tends to be visible on particularly active nights. It is softer, more diffuse than the green, often appearing as a faint crimson wash above the green curtains, like a deepening of the sky rather than a distinct structure. Nitrogen, which is abundant in the atmosphere, contributes its own colors. Blue and violet hues come predominantly from nitrogen molecules that have lost an electron entirely and then recaptured one, a slightly different process from simple excitation, but still governed by the same fundamental principle of energy release through photon emission. Purples appear where the outputs of oxygen and nitrogen mix, their individual colors blending at the edges of the curtains. The altitude of the aurora varies. Most of the visible aurora occurs between about 100 and 300 kilometers above the ground. But auroras have been detected as low as 60 kilometers, where the atmosphere is denser and the incoming particles lose their energy more quickly, and as high as 1,000 kilometers, in extreme cases, where the atmosphere is so thin that individual particles can travel enormous distances before striking anything at all. At 100 kilometers, in the densest part of the auroral zone, the incoming particles are stopped relatively quickly, depositing their energy over a short distance, producing a distinct lower edge to the aurora, a sharp, clearly defined lower border, often appearing as the bottom of the curtain. Higher up, where the atmosphere is thinner and the particles penetrate less effectively, the aurora fades more gradually, becoming softer and more diffuse toward its upper reaches. This is why the curtain shape is so characteristic. The bottom edge is sharp because that is where the particles are stopped, where the atmosphere is dense enough to absorb their energy in a concentrated zone. The top is soft because above that zone, the collisions become rarer, the light more scattered, the boundary less defined. You are looking at the profile of an atmospheric collision zone, drawn in light across the sky. And all of this happens in silence. There is no sound to the aurora, at least no sound that science has conclusively agreed upon. The aurora is light, pure and simple. Photons released by electrons returning to their resting state, multiplied by the trillions, carried down through 100 kilometers of air to reach the dark ground below. Each photon was born in a moment of return. A particle that had been excited, elevated beyond its natural state, and then released, falling back to where it belonged and giving off light in the process. It is, when you consider it slowly, a kind of poetry written in physics. The entire sky, lit by the simple act of things returning to rest. Something easy to forget, when you are watching the aurora in the cold dark of a winter night, is that you are not simply witnessing a light show. You are standing beneath a heater. The aurora is not just luminous, it is energetic. The charged particles raining down from the magnetosphere carry kinetic energy, and when that energy is deposited into the upper atmosphere through the collisions we have been describing, not all of it becomes light. A significant portion becomes heat. The thermosphere, that high, thin layer of atmosphere where the aurora lives, is warmed by auroral activity, sometimes dramatically so. During strong geomagnetic storms, the temperature of the upper atmosphere can rise by hundreds of degrees. Not at the surface, where we live, the thermosphere is far too thin to conduct that heat downward in any meaningful way, but up there, in that rarefied space above the weather, the aurora is a genuine source of warmth. This heating has effects. It causes the upper atmosphere to expand, to puff outward slightly, like a material warming and swelling. And this expansion has practical consequences. Satellites orbiting in low Earth orbit, the region from a few hundred to a few thousand kilometers above the ground, move through this upper atmosphere, and even the tiniest increase in atmospheric density at those altitudes creates more drag on a spacecraft. Satellites slow slightly. Their orbits decay a little faster than they otherwise would. Operators have to account for this, to plan around it, to occasionally fire thrusters to compensate. The Aurora, beautiful as it is, has a cost, a small but real tax levied on the technology we have placed in its neighborhood. The composition of the atmosphere matters enormously to what the aurora looks like, and we have touched on this already, but it is worth dwelling on for a moment, because the relationship between atmospheric chemistry and auroral color is one of the more elegant things about the whole phenomenon. The atmosphere is not uniform. It does not have the same mixture of gases at all altitudes. Near the surface, it is predominantly nitrogen, about 78%, with oxygen making up most of the remainder. But as you rise, the heavier molecules settle lower, and the composition shifts. By the time you reach auroral altitudes, molecular nitrogen is still present, but atomic oxygen, individual oxygen atoms rather than the paired molecules we breathe, becomes increasingly dominant. And higher still, hydrogen and helium, the lightest elements, make up a larger proportion. Each of these gases responds differently to particle bombardment. Each has its own set of possible excited states, its own characteristic photon energies, its own palette of colors it is capable of producing. The aurora is, in a very literal sense, a chemical fingerprint. If you could analyze the spectrum of the light precisely enough, break it apart into its component wavelengths, you would be reading the composition of the atmosphere at different altitudes, as clearly as if you had sent up a probe with a jar to collect samples. Scientists use exactly this technique to study the upper atmosphere remotely. Spectrometers pointed at the aurora can tell researchers not just what gases are present, but how they are behaving, what temperatures they are at, what pressures, how the energetic particle input is distributed. The aurora is simultaneously a spectacle and an instrument, a phenomenon and a measurement. Now we need to go somewhere deeper. Into the physics of the aurora that took scientists a very long time to understand, and that, even now, contains surprises. For much of the 20th century, the basic picture of the aurora was reasonably well established. Solar wind particles enter the magnetosphere, are guided by magnetic field lines to the polar regions, collide with atmospheric atoms, produce light. Clean, logical, satisfying. But as instruments improved and measurements became more precise, it became clear that this picture was incomplete. The particles arriving at auroral altitudes were moving too fast. They had more energy than the solar wind alone could account for. Something was accelerating them. Something was giving them an extra push somewhere between the outer magnetosphere and the top of the atmosphere. Finding out what that something was turned out to be one of the more fascinating detective stories in modern space physics. To understand the answer, we need to start with something that happens far above the aurora, in the outer reaches of the magnetosphere, where the geometry of Earth's magnetic field is constantly being distorted by the pressure of the solar wind. Imagine a rubber sheet, pulled taut. Now press your finger into it from one side. The sheet stretches, distorts, and if you press hard enough and then suddenly release, it snaps back. The energy stored in the tension is released all at once in a wave that propagates across the sheet. The magnetic field does something analogous. When the solar wind pushes against the magnetosphere, when a coronal mass ejection compresses it suddenly, when the field lines on the night side of the Earth stretch and then reconnect, a process called magnetic reconnection, in which field lines literally snap apart and join to new partners in a catastrophic reconfiguration, that snap releases energy. And that energy travels through the magnetized plasma of the magnetosphere as a wave. Not a sound wave, and not a light wave, but something that can only exist in a magnetized plasma. A wave that carries energy along the direction of the magnetic field, oscillating as it goes, sending ripples of electric and magnetic variation propagating through the charged gas of the magnetosphere. These are called Alfvén waves, named for the Swedish physicist Hannes Alfvén, who predicted their existence mathematically in 1942 and received the Nobel Prize for the work in 1970. Alfvén waves are, in a sense, the magnetic field singing. They carry energy from regions of disturbance, from the reconnection zones on the night side of the magnetosphere, from the boundaries where the solar wind pushes hardest, inward and downward along the field lines toward Earth. They are the medium through which the magnetosphere communicates its disturbances to the lower atmosphere. And they play a more direct role in the aurora than anyone initially suspected. The waves form primarily in a region of the magnetosphere called the plasma sheet, a broad, flat zone of relatively dense plasma that stretches across the night side of the Earth, sandwiched between the field lines that arc over the poles. This is where the energy of solar wind interaction is stored and then released, where reconnection events send Alfvén waves racing inward along the field lines toward the polar atmosphere. As these waves travel, they carry with them oscillating electric fields, and it is these electric fields that turn out to be the key. Think of a wave on the surface of the ocean. A cork floating on the water doesn't just bob up and down as the wave passes, it also moves slightly forward, carried by the wave's motion. Something similar happens to electrons in the path of an Alfvén wave. If an electron is moving in roughly the right direction at roughly the right speed, the oscillating electric field of the wave can couple to it, can lock onto it and carry it along, like a surfer caught by a wave and swept forward with it. This mechanism is called Landau damping, though the aurora-specific version of it has been studied in detail only relatively recently. In essence, electrons that are moving at just the right velocity, in resonance with the wave, are preferentially accelerated by it. They ride the electric field component of the Alfvén wave, gaining energy as they go, in much the same way that a surfer gains speed by staying in the right relationship to a breaking wave. The wave gives up some of its energy to the electron. The electron moves faster. And faster electrons, arriving at the atmosphere with more energy, produce a brighter, more energetic aurora. This surfing mechanism is elegant, but it is not the only way the magnetosphere accelerates electrons. There is another mechanism, one that operates differently, and in a different location, and that was discovered through a combination of satellite observation and pure theoretical reasoning. Consider what happens when you have a region in space where the density of charged particles is very different on one side versus the other. The magnetosphere is full of such regions, boundaries between different plasma populations, where the density, temperature, and velocity of particles change abruptly. Across these boundaries, electric fields can develop spontaneously, as the different particle populations interact and the magnetic field constrains how they can move. Under the right conditions, these electric fields can point in the direction of the magnetic field lines, parallel to them, rather than perpendicular. Parallel electric fields are particularly effective at accelerating electrons along the field line, toward the atmosphere. They act like a battery, building up a voltage difference across a region of space, and then driving electrons through that potential difference, giving them energy the way a battery drives current through a circuit and gives energy to whatever that circuit powers. This space battery mechanism operates at a specific range of altitudes, roughly between about 3,000 and 12,000 kilometers above the Earth's surface. Not in the outer magnetosphere, and not at auroral altitudes, but in between, in a region that came to be called, by the scientists who first identified it, the auroral acceleration region. The identification of this region was one of the defining achievements of space physics in the latter half of the 20th century. It required satellites capable of making precise measurements of electric fields and particle velocities at the right altitudes, and the data they returned was startling. Electrons were found to arrive at the top of the atmosphere with energies that were far, far higher than the background plasma could explain, electrons moving at velocities of tens of thousands of kilometers per second, which is a significant fraction of the speed of light. Not the full speed of light, but a meaningful fraction. These were particles that had been seriously accelerated. Pinpointing the altitude of the accelerator was a matter of careful measurement across multiple satellite missions over several decades. Researchers compared the energies of electrons at different points along the field line, working out from the data where the energy gain was occurring. The answer came back consistently. The bulk of the acceleration happens in that region between 3 and 12,000 kilometers, in the auroral acceleration region, above the visible aurora but well below the outer magnetosphere where the waves originate. For a long time, the mechanisms described by theorists to explain this acceleration, the parallel electric fields, the wave-particle interactions, remain theoretical. They were supported by satellite data, but they had never been reproduced experimentally, never tested in a laboratory setting in a way that would definitively confirm the physics. That changed in the early 2020s. Researchers at the Large Plasma Device at UCLA, a facility designed specifically to study the physics of plasmas under controlled conditions, successfully generated alphane waves in the laboratory and demonstrated directly that those waves accelerated electrons through the surfing mechanism in exactly the way theory predicted. The experiment was not able to replicate the full scale of the magnetosphere, of course. No laboratory on Earth could do that. But it validated the fundamental physics with a precision and directness that satellite observations alone could never quite achieve. It was a moment of confirmation that brought together decades of theory and observation. The mechanism that accelerates electrons to produce the aurora had been inferred from space, tested with satellites, described mathematically, and now demonstrated experimentally, in a room, in a machine, by scientists who could control the variables and watch exactly what happened. The aurora, it turns out, is not merely a product of the solar wind falling gently into the atmosphere. It is the output of a complex, multi-stage acceleration process, a cascade of energy that begins with a disturbance on the sun, propagates across 150 million kilometers of space, enters the magnetosphere, generates waves, builds electric fields, accelerates particles through mechanisms that blend wave physics and electromagnetic theory, and finally delivers those particles to the top of the atmosphere where they produce, in their collisions with oxygen and nitrogen, the light that reaches your eye on a clear night in the far north. There are very few things you can see with the naked eye that involve physics this layered. Most beautiful things in nature are beautiful in simple ways. The aurora is beautiful in a way that goes all the way down, layer after layer of elegant mechanism, each one more surprising than the last, each one discovered only through decades of painstaking work by scientists who were willing to follow the question wherever it led. And still, despite everything we know, standing beneath the aurora on a cold, clear night and watching it move, watching it ripple and surge and fold and brighten in waves that seem almost to breathe, it does not feel like physics. It feels like something else entirely. It feels like a reminder that the universe is stranger and more generous than we had any right to expect. The magnetosphere is not a static structure. It breathes, in a sense, expanding and contracting in response to the solar wind, flexing under the pressure of incoming particle streams, reshaping itself over minutes and hours as conditions in space change. And on the night side of the Earth, the magnetosphere does something particularly dramatic. It stretches. The solar wind doesn't just push against the sunward face of the magnetosphere and stop. It flows around the planet, and as it does, it drags the magnetic field along with it on the night side, pulling it outward into a long, extended tail, the magnetotail, that stretches away from the Earth in the direction opposite the Sun for millions of kilometers, far beyond the orbit of the Moon. This tail is not simply a passive extension. It is a reservoir of stored energy, a place where magnetic field lines are constantly being stretched and compressed and eventually reconnected, where vast currents flow through thin sheets of plasma, and where the conditions for auroral activity are, in large part, determined. When the magnetotail becomes sufficiently loaded with energy, when the field lines have been stretched as far as they can go and the stored energy reaches a critical threshold, something gives. The tail undergoes what scientists call a substorm. The stretched field lines snap back toward Earth in a process of rapid reconnection, releasing the stored energy explosively, sending it surging toward the polar atmosphere along the field lines. The aurora, which may have been quietly glowing for hours, suddenly blazes. A bright arc appears and rapidly brightens. New structures emerge and spread. The display intensifies and expands within minutes, driven by the energy released from the snapping tail. The substorm cycle, build-up, onset, recovery, is one of the fundamental rhythms of auroral activity. On active nights, multiple substorms can occur in sequence, each one producing a new surge of brightness, a new wave of intensity that moves through the auroral oval. From the ground, the watcher sees the aurora flare and dim again, unpredictable in its precise timing, but following this underlying pattern of energy loading and release. The magnetotail is, in this sense, the engine of much of the aurora's dynamism. It is where the energy is stored. It is where the trigger is pulled. Now, one of the ways scientists have come to understand the aurora most clearly is through a shift in how they think about it, not just as a light display, but as something more fundamental. The aurora is not simply what happens when particles hit the atmosphere. More precisely, the aurora is the optical signature of electrical currents flowing through the upper atmosphere. This distinction matters, because it reframes what you are looking at when you see the northern lights. The magnetosphere is threaded with currents, vast flows of electric charge moving through the plasma along specific pathways. Some of these currents flow along the magnetic field lines, connecting the outer magnetosphere to the ionosphere, the electrically conductive layer of the upper atmosphere. These are called field-aligned currents, and they are the channels through which energy flows from the magnetosphere to the atmosphere. When those currents are strong, when charge is flowing rapidly along the field lines, the particle precipitation is intense, the atomic excitation is vigorous, and the aurora is bright. When the currents weaken, the aurora dims. Seen this way, the aurora is a map of where currents are flowing. Its shape and brightness trace the electrical structure of the magnetosphere. The arcs, the curtains, the patches, each one corresponds to a region where current is descending from space into the atmosphere. Scientists studying the aurora are, simultaneously, studying the electrical state of near-Earth space. This perspective has been enormously useful for understanding and predicting how the aurora behaves. It connects ground-based observations to spacecraft measurements in a coherent framework, allowing researchers to cross-reference what they see from below with what satellites measure from above. Most of the particles responsible for the aurora are electrons. This is what we have been describing, electrons accelerated down the field lines, energized by waves and parallel electric fields, delivering their energy to atmospheric atoms through collisions. But electrons are not the only particles involved. Protons, the positively charged particles that make up the nuclei of hydrogen atoms, also participate, and they produce a distinct type of aurora by a distinctly different mechanism. Protons arriving from the magnetosphere travel down the field lines much as electrons do, but they carry far more mass. A proton is nearly 2,000 times heavier than an electron, and this mass difference changes how it interacts with the atmosphere. When a fast-moving proton enters the upper atmosphere, it can capture an electron from a neutral atmospheric atom, becoming, briefly, a neutral hydrogen atom itself. This newly neutral atom is no longer subject to the magnetic field, since the field only acts on charged particles, and so it continues moving in a straight line rather than following the field line. A moment later, the hydrogen atom loses its captured electron through a collision, becomes a proton again, gets deflected back to follow the field line, captures another electron, and so on, zigzagging downward through the atmosphere in a kind of charge exchange dance. During this process, the captured electrons are in excited states and emit light when they return to their ground state, producing what is known as proton aurora, or hydrogen aurora. The light comes predominantly in ultraviolet wavelengths, largely invisible to the naked eye, but detectable by instruments. Proton auroras tend to be broader and more diffuse than electron auroras, without the sharp, structured arcs that characterize the brightest visible displays. They form a diffuse background glow that underlies the more dramatic electron aurora, quietly contributing to the total auroral energy budget even when the sharper features get all the visual attention. There is another process that adds to the richness of the aurora, one that is less immediately obvious but plays a real role in the overall light produced. When a high-energy electron strikes an atmospheric atom or molecule, it does not always simply excite the atom and bounce away. Sometimes the collision is energetic enough to knock another electron entirely free of the atom, a process called ionization. This liberated electron is called a secondary electron, and it enters the atmosphere with its own energy, smaller than the primary that created it but still capable of causing excitation and further ionization. A single high-energy particle from space can, through this cascade of primary and secondary interactions, excite dozens or hundreds of atmospheric atoms before all the energy is finally absorbed. This multiplicative process, primary particle producing secondaries, secondaries producing their own excitation, is part of why the aurora can be as bright as it is. The initial particle is, in a sense, more efficient than it would be if it simply deposited its energy in one place. It spreads the interaction through a column of atmosphere, producing light at multiple altitudes, and the net result is a glow that is brighter and more volumetric than a simple one-to-one collision model would predict. The energy of the electrons involved in auroral precipitation spans a considerable range. At the lower end, electrons carry energies of perhaps a few hundred electron volts, enough to excite atmospheric atoms but not much more. At the upper end, the most energetic auroral electrons reach energies of around 10,000 electron volts, 10 kiloelectron volts, which is enough to penetrate significantly deeper into the atmosphere before being stopped. These high-energy electrons produce aurora at lower altitudes, contributing to the sharp lower border of bright auroral arcs, and they also produce harder radiation, X-rays, in fact, through a process called Bremsstrahlung, or breaking radiation, as they are rapidly decelerated by atmospheric molecules. Balloon experiments have detected these X-rays from above the weather layer, below the aurora itself. The balloons float at altitudes of perhaps 30 kilometers, far below the visible aurora, but close enough that the X-rays produced by the most energetic precipitating electrons reach them. For scientists, these X-ray measurements have been a useful diagnostic tool, a way of measuring what the energetic end of the electron population is doing without needing a spacecraft at auroral altitudes. The acceleration of electrons toward the atmosphere takes multiple forms, and scientists have found it useful to organize the aurora into two broad classes, based on how the electrons were energized and what the resulting aurora looks like. The first class is driven predominantly by the Alfvén wave mechanism, by the wave-particle interaction, the electron surfing process, that we explored in some detail earlier. Alfvén wave-driven aurora tends to be more dynamic, more rapidly changing, associated with the active phases of substorms and with conditions of strong solar wind driving. It is the kind of aurora that blazes and shifts rapidly, that produces the most dramatic visual dynamics, that leaves observers turning in circles trying to watch it all at once. The second class is driven primarily by quasi-static electric fields, the space battery mechanism, the parallel electric fields that build up across regions of the acceleration zone and drive steady currents of electrons downward. This type of aurora is somewhat more stable, more persistent, less prone to the rapid flickering and surging of the Alfvén-driven variety. It can produce steady arcs that hang in the sky for extended periods, glowing with quiet consistency while the more dynamic forms evolve around them. In practice, real auroras are often a mixture of both. The two mechanisms operate simultaneously, sometimes in the same region of sky, and distinguishing their contributions requires the kind of detailed particle measurements that only spacecraft can provide. But understanding the distinction has been important for building an accurate picture of how the aurora works, not as a single phenomenon driven by a single cause, but as a complex system with multiple modes and multiple energy sources, each contributing its own character to the display. The most visually striking form of the aurora, the one that appears in most photographs and has inspired most of the art and myth surrounding the lights, is what scientists call the discrete aurora. This is the aurora of curtains and arcs, of defined edges and clear structure, of ribbons that fold and move across the sky with fluid grace. Discrete auroras are bright, sometimes dramatically so. On active nights, a discrete auroral arc can be bright enough to read by, bright enough to cast shadows, bright enough that its light reaches the snow-covered ground and makes the whole landscape glow green. The brightness of discrete aurora is a direct reflection of the intensity of the field-aligned current driving it. Where the current is strongest, where the most electrons are descending along the field line per unit time, the aurora is most intense. Regions of peak current density appear as the brightest cores of the arcs, with brightness falling off toward the edges as the current diminishes. The internal structure of an auroral arc is often more complex than it appears from a distance. What looks like a single ribbon of light can, on closer inspection, or when viewed with instruments capable of high spatial resolution, reveal multiple parallel subarcs, striations, and fine structure that speaks to the organized nature of the current system producing it. The field-aligned current does not flow uniformly across the arc but is organized into structures that reflect the underlying geometry of the magnetospheric source region. As the magnetosphere evolves over the course of a substorm or a geomagnetic storm, the arcs move. They drift equatorward during the quiet growth phase, then surge poleward as the substorm onset releases the stored energy. They can split and multiply, a single arc dividing into two or three, each one moving independently, each one corresponding to a separate current filament in the magnetosphere. They can develop waves along their length, undulations that travel from one end of the arc to the other, making the curtain ripple and flutter. These transverse waves propagate at speeds and wavelengths that encode information about the plasma conditions in the region of space where the arc originates. Watching these wave patterns move through an auroral arc on a particularly active night is one of the more extraordinary things a person can witness with unaugmented eyes. The mathematics of plasma waves is written right there in the sky, playing out in real time, visible without any instrument other than the eyes you were born with. Now let us turn to color, because nothing about the aurora is more immediately striking to a first-time observer than the colors, and nothing is more precisely explained by physics. We have already touched on the basic principle that different gases emit different colors when their electrons are excited and return to their ground states. But the full picture of auroral color is richer and more nuanced than that simple summary suggests, and it is worth laying out carefully, because the colors of the aurora are not arbitrary. They are as specific and reproducible as the spectral lines in a chemistry laboratory. They are, literally, the signature wavelengths of specific atomic and molecular transitions, each one a fingerprint of a particular element in a particular state at a particular altitude. The dominant color in most auroral displays is green, a vivid, cool, electric green that sits at a wavelength of 557.7 nanometers. This is produced by atomic oxygen, individual oxygen atoms, not the paired molecules we breathe, at altitudes between roughly 100 and 150 kilometers. The physics behind this particular emission is interesting in itself. The transition that produces 557.7 nanometer green light is what physicists call a forbidden transition. At normal atmospheric densities, an atom in this particular excited state would almost immediately be bumped back to its ground state by a collision with another atom before it could emit the photon. But at auroral altitudes, the atmosphere is thin enough that the atom can persist in the excited state long enough, about a second, to emit the photon spontaneously. The green of the aurora is light that could only be produced in a very thin atmosphere. At sea level pressure, it would never appear. Red aurora comes from the same element, atomic oxygen, but from higher altitudes, typically 200 kilometers and above, where the atmosphere is thinner still. At these heights, the excited oxygen atom persists in its state even longer, for more than a minute, in some cases, before emitting. The transition produces light at 630 nanometers, firmly in the red part of the spectrum. Red aurora tends to be diffuse and soft because the emitting atoms are spread over a very large altitude range and the individual photon counts per unit volume are lower. On strong geomagnetic storm nights, the red aurora can appear as a vivid crimson or deep scarlet wash over the upper part of the sky, above the green curtains, giving the display a layered, almost painterly quality. Blue and purple hues come primarily from molecular nitrogen molecules that have been ionized by the incoming particles, stripped of an electron, and then recaptured one while still in an excited state. The transitions these excited nitrogen ions make as they relax produce light in the blue and violet range, typically below about 100 kilometers, where molecular nitrogen is abundant. These colors are often subtle. They can be lost against the brightness of the green and require either very transparent air, a very sensitive eye, or a camera to capture clearly. The mixing of these colors at the lower border of bright auroral arcs, where green and blue and violet overlap in a narrow zone, produces the characteristic purplish-pink fringe that experienced aurora watchers recognize as one of the signals that a particularly energetic display is underway. It is beautiful in its own right, but it also tells you something. The electrons arriving at those altitudes are energetic enough to drive nitrogen emissions alongside the dominant oxygen green, which means the acceleration above was working hard. Pink aurora sometimes appears at the very bottom of strong arcs, a soft, rosy color that blends the crimson of low-altitude oxygen red emission with the blues of nitrogen. It tends to appear and disappear quickly, a fleeting accent at the base of the curtain during the most intense moments of a display. The color you see also depends on conditions you might not think of as part of the aurora itself. The darkness of your sky matters. Light-polluted skies wash out the fainter colors. The sensitivity of your eyes matters. Human eyes are relatively poor at distinguishing color in dim light, and many people initially see the aurora as white or gray before their eyes fully adapt. What cameras capture and what eyes perceive can be quite different, partly because camera sensors are more uniformly sensitive across the spectrum than human vision, and partly because long exposures accumulate light that the eye cannot integrate in the same way. Some of the most spectacular photographs of the aurora show colors that were present but faint, real, physically accurate colors, genuinely there, but requiring more light gathering than the dark adapted eye can provide. The altitude, the chemistry, the particle energies, the atmospheric density at each layer, all of it is written in the colors, if you know how to read them. The aurora is, among many other things, a spectrometer the size of the sky. And it is painting with atoms. Using the specific palette of energies available to oxygen and nitrogen and hydrogen at the particular pressures and temperatures found in the upper atmosphere, a palette that cannot be changed, that has been the same for as long as this planet has had an atmosphere and a magnetic field, to produce, night after night, a display that is never the same twice. The colors are fixed. The display is infinite. There is something quietly wonderful in that combination. There is a kind of precision hidden inside the aurora's beauty that rewards attention. The colors are not random. They are not the aurora choosing, in some poetic sense, what mood it is in tonight. Each color is a direct consequence of specific physics operating at a specific altitude, a one-to-one correspondence between what you see and what is happening chemically and physically at that point in the atmosphere. Once you understand the logic, the sky becomes legible. Not less beautiful, more so, because you are reading something real. Green is where most people begin, because green is where the aurora most often begins. That vivid, unmistakable color, cool and luminous, a color that has no real equivalent in ordinary earthly experience, comes from atomic oxygen. Not the molecular oxygen we breathe, paired and stable, but individual oxygen atoms, broken apart from their usual partnerships by the energetic conditions of the upper atmosphere. These atoms sit at altitudes of roughly 100 to 300 kilometers above the ground, and when they are struck by incoming electrons and elevated to an excited state, they eventually release a photon at precisely 557.7 nanometers. That wavelength is green. Always green. The laws of atomic physics do not vary. The reason this particular color dominates most auroral displays is partly chemistry and partly geometry. At those altitudes, 100 to 200 or 300 kilometers, atomic oxygen is abundant. Conditions are right for the relevant excited state to persist long enough to emit, and it is also the altitude range where most of the auroral particle precipitation is concentrated. The green aurora is, in effect, the aurora at its most efficient. It is what happens when the system is running at its most typical. And it is a green unlike any green produced by vegetation or paint or glass. It has a quality of luminosity, of light coming from within the thing rather than being reflected off it, That gives it an almost supernatural appearance in photographs and an even more unusual quality in person, where the brain struggles to categorize it. It does not look like a colored light source the way a lamp does. It looks more like the sky itself has become the source, like the color is everywhere at once, filling a volume rather than emanating from a surface. At higher altitudes, above roughly 300 kilometers, something changes. The atmosphere is thinner, collisions between atoms are rarer, and the excited oxygen atoms that would produce green at lower heights instead have time to undergo a different transition. At these rarefied heights, oxygen emits at 630 nanometers, which is red. Deep, warm, crimson red, a color that could not be more different from the green produced by the same element 150 kilometers lower. Red aurora is less commonly seen than green, partly because the emissions are weaker, fewer atoms, lower density, and partly because the human eye is less sensitive to red light in dark conditions than it is to green. The red aurora is often present on active nights without being noticed, hanging above the green curtains as a soft, high-altitude wash that blends into the dark sky and requires a dark-adapted eye and a clear horizon to detect. Cameras tend to capture it more reliably than eyes do, which is part of why photographs of strong auroral storms often show far more red than observers on the ground reported seeing at the time. On the most powerful geomagnetic storm nights, the red aurora can become undeniable, a vivid scarlet that covers large portions of the sky, visible at latitudes far beyond the usual auroral zone. Historical accounts of the aurora seen at low latitudes, in medieval Europe, in the American South, in Japan, describe a deep red light in the sky that was frequently interpreted as fire, as blood, as divine warning. These were almost certainly red auroras, the high-altitude oxygen emissions spreading across a sky that would normally never see the lights at all, viewed by people who had no framework for understanding what they were seeing and drew on the most powerful imagery available to them. The red aurora is the aurora of extremity, of the most intense solar storms, of the magnetosphere under maximum stress. It is the aurora pushing beyond its usual home, reaching toward latitudes where it does not ordinarily belong, driven by forces that have temporarily overwhelmed the normal boundaries. There is a third kind of red, or more precisely, a dark reddish tone that appears at the very lower border of intense auroral arcs, below the green, forming a fringe that is subtle but distinctly different in character from the high-altitude red above. This lower border color, sometimes described as pink, sometimes as dark red, sometimes as a deep rose, is produced at altitudes below about 100 kilometers, where the atmosphere is dense enough that the excited oxygen atoms are collisionally quenched before they can emit the green photon. The energy is absorbed by the surrounding gas before it can produce the 557.7 nanometer emission. Instead, different transitions occur, and the result is light at different wavelengths, contributing to a color at the lower border that is distinct from what appears higher up. This lower border coloration is often one of the first things that experienced aurora observers watch for. Its appearance indicates that the incoming electrons are energetic enough to penetrate deep into the atmosphere, that the display is not just bright but genuinely powerful, driven by high-energy particle precipitation rather than the softer, lower-energy electrons that produce the typical green glow. It is a signature of intensity, a warning from the physics that something exceptional is happening. Blue and purple are the domain of nitrogen, and the story of how nitrogen produces these colors is slightly more involved than the simple excitation and emission that produces the oxygen colors. When an energetic particle strikes a nitrogen molecule, it can do several things. It can excite the molecule, elevate it to a higher energy state, in which case the molecule will emit light at wavelengths that depend on which transition it makes when it relaxes. Nitrogen molecules produce a wide range of emission wavelengths, contributing across much of the visible spectrum and strongly in the ultraviolet. But the most visually striking nitrogen contributions come from a specific process, ionization. When the incoming particle is energetic enough, it can knock an electron entirely free of the nitrogen molecule, creating a positively charged nitrogen molecular ion. This ion, suddenly in a new and unfamiliar state, is itself in an excited condition, and as it relaxes, it emits light, most characteristically in the blue-violet range. The first negative band system of nitrogen, as spectroscopists call it, produces emissions around 391 and 428 nanometers, firmly in the blue and violet. These are the colors that add depth and coolness to the lower portions of bright auroral arcs, that create the blue-tinged curtains that photographers prize, that give the display a complexity and range that pure oxygen emission alone could not produce. The blue and reddish-purple that nitrogen contributes appear at lower altitudes, roughly below 100 kilometers, where molecular nitrogen is most abundant and where the incoming particles are energetic enough to ionize it. This is why the lower portions of bright arcs tend toward blue and purple, while the middle sections glow green, and the upper reaches show red. The aurora is altitude-coded. If you know the color key, you can read the height of each part of the display directly from its color. Nitrogen also contributes emissions in what is called the first positive band, a set of transitions that produce light in the red and near-infrared range. Some of this falls within the visible spectrum, adding reddish tones in the lower portions of arcs that blend with the blue of the ionized nitrogen to produce purple. The mixing of nitrogen's blue-violet and reddish contributions, at the altitudes where both are active simultaneously, is one source of the deep purple tones that appear in the lower borders of particularly intense arcs. Purple, in the aurora, is often a hybrid, not a pure atomic emission but a blend of contributions, a color produced by the overlapping of multiple processes in the same region of sky. The eye and cameras see it as a single color because the photons of different wavelengths arrive together, but behind that apparent unity is a layered interplay of different atmospheric chemistry. Helium, which is present in the upper atmosphere in small but measurable quantities, can also contribute to the aurora's color palette under the right conditions. Helium emissions fall in the blue and purple range, overlapping with nitrogen's contributions and adding to the overall richness of the display's cooler color tones. Helium's contribution is modest. It is far less abundant than oxygen or nitrogen at auroral altitudes, but it is part of the full picture, part of the complete chemical story that the aurora tells about the atmosphere it moves through. Putting it all together, the altitude-color relationship of the aurora lays out something like this. Below about 100 kilometers, where the atmosphere is relatively dense and incoming electrons must be energetic to penetrate, blue and purple dominate, produced by ionized nitrogen molecules and their subsequent emission as they relax. The atmosphere here is thick enough that green oxygen emission is partially suppressed, and the blue-purple of nitrogen is what emerges most clearly. From roughly 100 to 300 kilometers, the broad middle layer, green atomic oxygen emission dominates. This is the home of the classic aurora, the altitude band where most of the particle precipitation occurs on typical nights, where the conditions for the 557.7 nanometer transition are most favorable, where most of the light that has ever been observed as the northern lights originated. Above 300 kilometers, and increasingly so above 400, the red of atomic oxygen takes over. Here the atmosphere is so thin that the longer-lived excited state responsible for the 630 nanometer transition can persist without being quenched, and the oxygen atoms glow in the red before falling back to their ground state. These boundaries are not sharp lines. They are gradients. The transitions from one color to another happen gradually, over ranges of altitude, and on any given night the display may emphasize one zone more than others depending on the energy spectrum of the incoming particles. A soft, low-energy precipitation produces a gentle green aurora, perhaps with hints of red high up. A hard, energetic precipitation drives deeper into the atmosphere, adds the blue-purple of nitrogen at the lower border, intensifies the overall brightness, and may push the red emission to altitudes low enough that it overlaps clearly with the green above. The display you see on any particular night is, in a very literal sense, a function of what the sun has been doing, what the magnetosphere has done with that input, what energies the electrons carry when they arrive at the top of the atmosphere, and where in that atmosphere they deposit their energy. The aurora is not just colored light. It is a diagnostic, a message written in wavelengths about conditions across a range of scales, from the surface of a star 150 million kilometers away to a layer of air 100 kilometers above your head. What is perhaps most striking about all of this is how consistent it is. These are not approximations. The green of the aurora at 150 kilometers is not similar to 557.7 nanometers. It is 557.7 nanometers, exactly, every time, everywhere in the world, whether the aurora is seen from Alaska or Norway or Antarctica. The red above 300 kilometers is always 630 nanometers. The blue-violet of ionized nitrogen is always in the same range. The physics does not vary by hemisphere or season or culture or century. The colors of the aurora are among the most precisely reproducible things in nature. They are as fixed and invariable as the elements that produce them. And they have been the same colors for as long as Earth has had a magnetic field and an atmosphere and a sun that sends its wind outward, billions of years of the same palette, painting skies that no human eye was present to see, long before there was anything alive on this planet that could look up and wonder what it meant. The aurora has been doing this without us. It continues to do it whether we are watching or not. On the far side of the planet right now, somewhere above the Antarctic, the same chemistry is unfolding in the southern sky, the same greens, the same reds, the same blue-purple fringes, in response to the same solar wind that moves the northern lights. The colors were never for us. But we get to see them anyway. Color in the aurora is not decoration. It is information. Every shade that appears in the sky above the polar regions is the direct result of a specific atomic or molecular transition occurring at a specific altitude under specific physical conditions. The palette is constrained, not infinite, not arbitrary, and within those constraints, the aurora produces combinations that can range from the quietly beautiful to the genuinely overwhelming. Above roughly 250 kilometers, the atmosphere becomes the exclusive territory of atomic oxygen. Below that altitude, molecular nitrogen and molecular oxygen are still abundant enough to compete, to contribute their own emissions, to add complexity to the mix. But above 250 kilometers, the heavier molecules have largely settled lower, and what remains is predominantly atomic oxygen, individual atoms, light and sparse, drifting in a near vacuum that is still, just barely, an atmosphere. In this rarefied region, atomic oxygen holds the stage entirely. And what it produces there, under the excitation of incoming electrons, is not the green that defines the aurora at lower heights. It is red. A specific, reproducible, unmistakable scarlet, the 630 nanometer emission that results from an excited oxygen atom undergoing a transition that simply cannot occur quickly enough at lower altitudes, where collisions interrupt it before the photon can be released. This scarlet red is the color of the aurora at its highest reaches. It is the color of the display seen from latitudes far below the polar regions when a geomagnetic storm of sufficient power expands the auroral oval southward and downward. When people standing in France, or Texas, or Japan have looked up on certain extraordinary nights throughout history and seen a red sky, a sky that appeared to be lit from within by something that had no obvious natural explanation, this is what they were seeing. The high-altitude oxygen emission, spread across a vast region of sky, visible not because the aurora had descended to lower altitudes but because the emitting layer above 300 kilometers was bright enough, and extensive enough, to be visible from far away. The red aurora is simultaneously the rarest commonly seen color and the one that has had the most dramatic effect on human history, precisely because it appears at times of maximum solar activity, when the sun is most disturbed, when the magnetosphere is under greatest stress, and because it is visible from places where the aurora is otherwise unknown. The records of red skies in medieval chronicles, interpreted as omens and portents, are almost certainly records of this high-altitude oxygen emission seen at its most extreme. What is particularly interesting about the relationship between the red and green oxygen emissions is that they are not cleanly separated in altitude. The layer that produces green, centered roughly between 100 and 200 kilometers, does not simply stop at its upper boundary and hand over to the red layer. There is a transition zone, a region where both transitions are possible depending on the local conditions, where the atmosphere is thin enough that the red emission becomes increasingly viable but not yet so thin that the green emission has vanished entirely. In this zone, both colors can be present simultaneously, and the mixing of red and green at these intermediate altitudes produces a blended appearance, sometimes orange, sometimes a warm yellowish tone, that is less commonly photographed and less commonly described but is a genuine feature of the aurora's color range. The red emissions also extend beyond the sharp upper boundary we might imagine. They do not simply switch off above a certain altitude. The excited oxygen atoms that produce red light are present, in decreasing numbers, well above 300 kilometers, all the way up through the upper thermosphere and into the transition region between the thermosphere and the exosphere, where the atmosphere shades gradually into the near vacuum of space. The aurora, at its very highest reaches, is still emitting red photons, just in diminishing quantities. The display trails off rather than ending abruptly, like the last notes of a piece of music fading rather than stopping. The precise wavelengths of the main auroral colors are worth knowing, because they reveal something about the orderly nature of atomic physics and how completely the aurora is governed by it. Green atomic oxygen, 557.7 nanometers. Red atomic oxygen, 630.0 nanometers, with a secondary line at 636.4 nanometers. The blue-violet of ionized molecular nitrogen, primarily 391.4 and 427.8 nanometers. Neutral nitrogen molecules contribute across a wide range, including both the visible blue-purples and significant emission in the ultraviolet, below 400 nanometers, which is invisible to the human eye but detectable by instruments. These wavelengths are the fingerprints of the aurora, the same anywhere in the solar system where oxygen and nitrogen exist in an atmosphere and are subjected to energetic particle bombardment. Astronomers studying aurora-like phenomena on other planets look for these same wavelengths, because the physics is universal. When the incoming electrons are particularly energetic, the high-energy primary electrons that penetrate deepest into the atmosphere, the ones that produce the X-ray Bremsstrahlung radiation detected by high-altitude balloons, they can drive a distinctive color at the very lower border of intense arcs. This color is sometimes described as a greenish-blue, or a teal, appearing at altitudes below 100 kilometers where the combination of high electron energy, dense atmosphere, and strong nitrogen ionization creates conditions that are different from those found higher up. The greenish-blue is not common. It requires genuinely energetic precipitation, but it is a real feature of the aurora's color palette, visible in photographs of the most intense displays and occasionally to the naked eye during the peak moments of a strong substorm. Nitrogen's contribution in the ultraviolet is worth noting even though it falls outside what human eyes can see. In the wavelength range between roughly 100 and 400 nanometers, the ultraviolet, nitrogen molecules and ions produce some of their most intense emissions. These ultraviolet auroras are invisible from the ground in any direct sense, but they are bright enough to be detected by instruments on spacecraft, and they have been used extensively to study the global structure of the auroral oval from orbit. A satellite equipped with an ultraviolet imager can photograph the entire auroral oval of the Earth, both poles simultaneously, a complete ring of light around each magnetic pole, in a way that no ground-based observer could ever see. From space, the aurora looks like a crown. These ultraviolet images have been scientifically invaluable. They show the shape and extent of the auroral oval in real time, allowing researchers to track how it expands and contracts in response to solar activity, where it is brightest at any given moment, and how the northern and southern ovals relate to each other. The ultraviolet aurora, invisible to the naked eye, has in some ways been more useful to science than the visible aurora, simply because it can be observed globally rather than locally. Purple and pink are the colors of mixture, of the aurora speaking in more than one voice simultaneously. Purple, as it appears in the aurora, is not produced by a single atomic transition. There is no single element that emits specifically purple light in the auroral context. Instead, purple arises from the overlap of blue nitrogen emission and red oxygen emission occurring in the same region of sky, their separate wavelengths combining in the eye or on the camera sensor to produce a color that neither element would produce alone. In regions where both nitrogen ionization and oxygen red emission are active at similar altitudes, which can happen under specific conditions of particle energy and atmospheric composition, the resulting blended color is purple. Pink arises in a similar way, but from a different combination. When green oxygen emission and the reddish contributions of nitrogen's first positive band system overlap, when the display is producing both colors in the same field of view, at altitudes close enough together that the eye cannot easily separate them, the result is pink. Sometimes this appears at the very base of an auroral arc, where the green is still present but the nitrogen emissions add a warmer, redder component. Sometimes it appears as a separate zone just below the green, in the transition region where different processes are simultaneously active. The visual appearance of white aurora is simply the result of these mixing processes taken to an extreme. When multiple emission lines, green, red, blue, violet, are all present simultaneously and roughly equally, when the display is bright enough that the eye's color discrimination is partially overwhelmed by the overall intensity, the result can look white or very pale. White aurora is not a distinct process, it is what happens when several processes coincide. It is the aurora in full voice, all its colors sounding at once and blending into something that the eye cannot fully resolve. Among the colors that the aurora produces, there is a rough hierarchy of rarity, though this hierarchy depends significantly on the latitude of the observer, the solar cycle phase, and how dark and transparent the sky is. Pale green is the most commonly seen auroral color by a considerable margin. For most people who see the aurora from the typical viewing zones, northern Scandinavia, Iceland, Canada, Alaska, on a typical active night, the display is predominantly green. The conditions for atomic oxygen emission at 100 to 200 kilometers altitude are met regularly, on any night with reasonable solar activity and a clear sky. Green is the aurora in its everyday form, the baseline from which everything else departs. Pink is perhaps the next most commonly observed color, particularly that soft, rosy pink that appears at the lower border of green arcs during moderate to strong displays. It is visible often enough that aurora watchers in good locations see it regularly, and it has a particular visual quality, delicate, warm, almost floral, that makes it memorable when it appears. It tends to flash in and appear briefly, during moments when the lower border of an arc intensifies, and it can fade just as quickly. But it is not rare. Red, in its high-altitude form, is less commonly seen, not because the physical conditions for it are unusual, but because the emission is dimmer than the green and requires good dark adaptation, a clear horizon, and a reasonably active night. With a camera on a long exposure, red appears in many photographs that were taken on nights when observers on the ground reported seeing none. It is there more often than it seems. The eye simply misses it. Blue and purple are rarer still, at least in their full, vivid form. They require energetic precipitation, high-energy electrons that penetrate to the altitudes where nitrogen ionization is efficient, and they tend to be visible for shorter periods, during the most active moments of a substorm, at the bases of the brightest arcs. Photographers often capture blue and purple in images from nights that produced only average visual impressions, because the camera is more sensitive to these wavelengths than the dark-adapted human eye. But to see vivid blue or deep violet with the naked eye, in the aurora, is a genuine experience, one that requires being in a dark, transparent sky during a strong display. The full-color aurora, a display that shows clear green, distinct red above, blue-purple at the lower borders, and the pinks and whites that come from mixing, is a relatively rare event even for regular aurora watchers. It requires a combination of strong solar activity, favorable geometry, a dark sky, and the right viewing location. When it happens, it is the kind of thing that stays with a person for a long time. Not just as a visual memory, but as something that adjusts the way you think about what the sky is capable of. The aurora does not owe anyone a full-color display. It gives what the physics allows, on the schedule that the sun and the magnetosphere set, in the colors that oxygen and nitrogen and the laws of atomic transitions determine. There is no negotiating with it, no predicting it with certainty, no guaranteeing that any particular night will produce anything more than a faint green arc low on the horizon. But on the nights when everything aligns, when the solar wind is right, when the magnetosphere responds, when the sky is dark and the air is clear, the full palette comes out, and the sky above the polar regions becomes something that no painting has ever quite captured, and no description has ever fully conveyed. It is, in the end, something you have to see to understand. And even then, understanding feels like the wrong word for what happens to you when you are standing beneath it. The aurora is not a northern phenomenon. It never was. While the Aurora Borealis has captured most of human imagination, written into the myths of Arctic peoples, documented by European scientists, photographed by countless travelers to Scandinavia and Canada, its mirror image has been quietly performing the same display at the opposite end of the Earth, over the frozen continent of Antarctica and the cold southern oceans, for exactly as long as the northern lights have been lighting the Arctic sky. The aurora australis, the southern lights, is not a separate phenomenon or a lesser one. It is the same process, driven by the same solar wind, organized by the same magnetospheric currents, producing the same colors through the same atomic physics. The two auroras are conjugate, meaning that they occur simultaneously, linked by the magnetic field lines that connect the northern and southern polar regions. When a substorm fires in the magnetosphere and sends a surge of electrons down toward the northern auroral oval, the same disturbance sends electrons down the conjugate field lines toward the south. The two ovals light up together, responding to the same trigger, at the same moment. Scientists have used this conjugacy as a research tool. By comparing simultaneous observations from both hemispheres, measuring whether the northern and southern auroras are truly mirror images or whether there are systematic differences between them, researchers can learn about the asymmetries of the magnetosphere, about how the geometry of the field differs between the two poles, and about how the solar wind interacts with the magnetosphere in ways that are not perfectly symmetric. The two auroras tell slightly different stories, and the differences between those stories are informative. For all that, the Aurora Australis is far less observed than its northern counterpart, and the reason is straightforward geography. The southern auroral oval sits primarily over Antarctica and the surrounding ocean, one of the most inaccessible and inhospitable places on Earth. There are no permanent civilian populations within the auroral zone in the southern hemisphere. There are research stations, McMurdo, Amundsen Scott South Pole Station, various national facilities maintained by countries with Antarctic research programs, and the scientists stationed there have produced remarkable observations of the southern lights. But the kind of regular, casual observation by travelers and local populations that has characterized the northern lights for centuries simply does not happen in the south. The southern lights are seen mainly by researchers, by the crews of ships crossing the Southern Ocean, and occasionally from the southern tips of the inhabited continents, Patagonia, Tasmania, the South Island of New Zealand, on the most active nights when the oval expands enough to reach those latitudes. This geographical asymmetry has given the northern lights an outsized place in human culture relative to their scientific equivalence with the southern lights. The stories, the myths, the art, the tourism, all of it has accumulated around the Aurora Borealis simply because there have always been people in the right places to see it. The best countries for viewing the northern lights are those that sit within or close to the auroral oval, that ring of auroral activity centered on the magnetic North Pole. Norway's northernmost region, Troms og Finnmark, is among the finest locations on the planet. The city of Tromsø sits at nearly 70 degrees north latitude, directly within the auroral zone, and offers the additional advantage of surrounding fjords and mountains that make for spectacular scenery even when the lights are not particularly active. Iceland, sitting astride the auroral oval, offers the lights from almost anywhere on the island on clear nights during the winter months, and Iceland's relative accessibility from Europe and North America has made it one of the most popular aurora tourism destinations in the world. Finland's northern region, Lapland, particularly the area around Saariselkä and the town of Rovaniemi, offers long, dark winter nights and landscapes of frozen lakes and snow-laden forests that give the aurora a setting of particular beauty. Sweden's far north, around Abisko and Kiruna, is known for a microclimate that produces unusually clear skies even when the surrounding region is cloudy, the result of the particular topography of the Torntrask Lake Valley. Northern Canada, Yukon, Northwest Territories, northern Manitoba, offers vast dark skies away from light pollution and sits comfortably within the auroral zone. Whitehorse and Yellowknife are established aurora viewing destinations, valued by visitors who want to combine the lights with the experience of genuinely remote northern wilderness. Alaska, in the United States, offers similar advantages. Fairbanks in particular, sitting under the auroral oval, is one of the consistently best places in North America for regular aurora observation. And across the northern edge of Russia, the lights are visible from communities along the Kola Peninsula and in Siberia, though these regions are less frequently visited by international travelers. What all of these places share is proximity to the auroral oval, reasonable accessibility, and enough dark winter nights to give visitors a realistic chance of seeing the lights. None of them can guarantee a display. That is not how the aurora works. Because here is something that surprises many people who travel specifically to see the northern lights. The aurora is always occurring, somewhere above the polar regions. It never truly stops. On any given night, even on the quietest nights of solar minimum, the auroral ovals glow with some level of activity. Electrons are always precipitating, always exciting atmospheric atoms, always producing at least a faint emission above the magnetic poles. The aurora does not switch on only during solar storms and switch off the rest of the time. What varies is the intensity and the extent. On quiet nights, the aurora is faint, confined to a narrow band close to the magnetic poles, and visible only under the darkest and clearest of skies. On active nights, it brightens and spreads. On storm nights, it can become extraordinary. But the threshold between invisible and visible, between a faint green glow that requires a camera to detect and a display that fills the whole sky and moves faster than the eye can follow, that threshold is governed entirely by conditions on the sun and in the magnetosphere, and those conditions are not predictable with any reliability beyond a day or two in advance. This is the thing that every aurora guide and every space weather forecaster will eventually tell you: the aurora is unpredictable. Not in the sense that we know nothing about it, we know a great deal. We know the solar cycle, we know the behavior of coronal mass ejections, we know how the magnetosphere responds to different types of solar wind input. But translating that knowledge into a reliable prediction of whether a given place will have a good display on a specific night remains genuinely difficult. Aurora chasers describe the lights as having a personality, as being, in a word some of them use, a diva. Temperamental. Capable of producing spectacular displays on nights when every forecast suggested modest activity, and capable of remaining invisible on nights when all the indicators pointed to something remarkable. The magnetosphere is a complex, nonlinear system, and complex nonlinear systems have a tendency to surprise you. This unpredictability is part of the aurora's particular hold on people. Unlike a scheduled event, unlike something you can plan to see and reliably experience, the aurora requires patience. It requires being in the right place and being willing to wait, sometimes for many nights, sometimes through clouds and mild weather and disappointing forecasts, for the right combination of solar activity, clear sky, and luck. When it finally appears, when you have waited through the disappointing nights and then stepped outside at midnight and found the sky alive with light, the response is not just aesthetic but visceral. The waiting has made it real in a way that a guaranteed spectacle never quite achieves. Geomagnetic storms are what push the aurora from remarkable to unforgettable, and from local to global. A geomagnetic storm is the magnetosphere's response to a particularly intense interaction with the solar wind. When a coronal mass ejection arrives and its magnetic field is oriented in the right way, southward, opposing Earth's northward pointing field, the two fields interact most strongly. The solar magnetic field and Earth's field connect and reconnect across the boundary between them, a process called magnetic reconnection at the magnetopause, and energy floods into the magnetosphere at a much higher rate than during quiet conditions. The magnetosphere is compressed, distorted, energized. The auroral oval expands and brightens. The particle precipitation intensifies. Geomagnetic storms are rated on a 5-point scale, G1 through G5, with G1 being a minor storm and G5 being an extreme event. G1 and G2 storms are relatively common, occurring multiple times per year during active phases of the solar cycle, and they produce good auroral displays visible from the usual viewing locations. G3 and G4 storms are rarer and push the aurora to noticeably lower latitudes, visible from Scotland and the northern United States as well as the typical auroral zones. G5 storms are rare and powerful, events that occur perhaps a few times per solar cycle, and they can push the aurora all the way to the tropics on the most extreme occasions. The May 2024 geomagnetic storm, one of the strongest in 2 decades, was rated G5, and it produced auroral displays visible across large parts of the continental United States and Europe, across Central Asia, across parts of Australia and New Zealand. People who had never seen the northern lights in their lives stepped outside on those nights and found the sky above them streaked with color. Social media filled with photographs taken from latitudes where the aurora had not been photographed for many years. It was a reminder, vivid and immediate, that the boundary of the auroral zone is not a permanent fence but a line that the sun can move at will. But the aurora's power is not simply aesthetic. As the storm expanded the display across the sky, it was also doing something less beautiful and more practical, interfering with technology. The same energy that produces the aurora, the currents flowing through the ionosphere, the particles precipitating into the upper atmosphere, the distortion of Earth's magnetic field, also interacts with human systems in ways that range from inconvenient to damaging. Radio communications are among the first things affected. The ionosphere, which the aurora illuminates, is also the layer of atmosphere that reflects certain radio frequencies back to Earth, enabling long-distance radio communication. During geomagnetic storms, the ionosphere becomes irregular and turbulent. Radio signals that would normally propagate reliably across thousands of kilometers become absorbed, distorted, or reflected at unpredictable angles. High-frequency radio communications, used by aviation, by maritime navigation, by amateur radio operators, by certain military systems, can be degraded or blocked entirely for hours during strong storms. GPS and other satellite navigation systems are also vulnerable. The signals from GPS satellites must pass through the ionosphere on their way to receivers on the ground, and the irregularities in the ionosphere during a storm introduce errors in the time delay of those signals, errors that translate directly into positional errors. For most users, a GPS accuracy degradation of a few meters is an inconvenience. For precision agriculture, for surveying, for aircraft navigation using GPS approaches in poor visibility, the degradation can be more consequential. Satellites themselves face increased risk during geomagnetic storms. The heating of the upper atmosphere that the aurora drives, the expansion of the thermosphere that we noted earlier, increases atmospheric drag on low-orbit satellites. Orbits decay faster. Station-keeping fuel is consumed more rapidly. On the most extreme storm nights, mission operators have to actively manage their spacecraft's trajectory to compensate for the increased drag. Power grids on the ground can also be affected, through a mechanism called geomagnetically induced currents. The fluctuating magnetic field during a storm induces electrical currents in long-conducting structures, pipelines, rail lines, and most significantly, the long transmission lines of electrical grids. These induced currents are not like the alternating current that power systems are designed to handle. They are quasi-DC, slow, steady flows that can saturate the cores of transformers, causing them to overheat and potentially fail. The 1989 geomagnetic storm caused the complete collapse of the Hydro-Quebec power grid in Canada within 90 seconds of the storm's peak, leaving 6 million people without power for up to 9 hours. Transformer damage was extensive. The tension here is a genuinely interesting one. The same phenomenon that compels people to book flights to Norway and stand in the cold of a Finnish night, necks craned upward, hoping that same phenomenon can, under the right conditions, shut off the lights for an entire city. The beauty and the disruption come from the same source, through the same mechanism, as an inseparable pair. The aurora is not the disruption's pretty face. They are the same thing, seen from different angles. Understanding the aurora is, in this sense, not just about understanding something beautiful. It is about understanding a natural system that is coupled to the infrastructure of modern civilization in ways that matter. The more we depend on satellite communications, on precision navigation, on interconnected power grids with long transmission lines, the more we need to understand what the sun does and how the magnetosphere responds. Space weather forecasting exists because the aurora exists, because the same physics that makes the lights dance also makes transformers fail and GPS signals drift. We watch the sun carefully now. We have spacecraft dedicated to monitoring the solar wind, measuring its speed and density and magnetic field orientation in real time. We have models of the magnetosphere that attempt to predict how it will respond to incoming disturbances. We have alert systems that notify power grid operators and satellite controllers when a significant storm is on its way. And on the nights when those alerts go out, when the models are predicting a G3 or G4 or G5 event, when the solar wind data shows a strong southward magnetic field bearing down on the magnetosphere, the same notification reaches, through apps and websites and social media, the people who will drive to the darkest spot they can find, wrap themselves in their warmest clothes, and wait. The engineers and the dreamers, both watching the same sky, both waiting for the same lights. For a long time, it was considered folklore. People living in the high Arctic, the Sami of northern Scandinavia, the Inuit of Canada and Alaska, communities whose lives had been organized around the northern landscape for generations, had long described hearing the aurora. A faint hissing, a soft crackling, a delicate sound accompanying the brightest moments of the display, as though the lights themselves were breathing audibly. These accounts were consistent across cultures and centuries. Different peoples, describing the same thing, in the same way. Scientists were skeptical. The aurora occurs at altitudes of 100 kilometers and above. Sound cannot travel from that height to the ground in any meaningful way. The atmosphere between the aurora and the surface is too thin to carry it, and the distances involved are simply too great for any direct acoustic connection. The physics seemed to rule it out. The accounts were chalked up to imagination, to suggestion, to the human tendency to fill sensory gaps when the visual experience is overwhelming enough. And then the recordings were made. Finnish researchers, studying the auroras systematically in the early 21st century, placed sensitive microphones in the dark, still air of auroral nights and listened. What they captured were faint but distinct sounds, crackling, clapping, quiet hissing, occurring at the same moments that the aurora was most active overhead. The sounds were not coming from 100 kilometers up. They were coming from about 70 meters above the ground. What appears to happen is this: during geomagnetic storms, the same conditions that power the aurora above also affect the atmosphere much closer to the ground. Temperature inversions, layers where warm air sits above cold air, can form in the lowest part of the atmosphere, the boundary layer just above the surface. When the geomagnetic conditions are right, electrical charges can build up and discharge within these layers, producing the faint crackling and hissing that observers have reported for centuries. The sounds are not the aurora itself, exactly, not sound waves traveling down from the light. They are a low-altitude electrical response to the same conditions that produce the light, occurring independently but simultaneously. The folklore was not wrong. It was simply describing a real phenomenon for which the mechanism took a long time to find. The people who said they could hear the aurora were hearing something. Something quiet, something easily masked by wind or other ambient noise, but real, a faint electrical whispering in the cold air of the polar night. There is something satisfying about that. A piece of traditional knowledge, held for centuries in communities that lived close to the phenomenon, eventually confirmed by instruments. The aurora, it turns out, does not just speak to the eye. The tools scientists use to study the aurora today span an extraordinary range of scales, from individual photon detectors pointed at a narrow patch of sky to spacecraft measuring the magnetosphere from thousands of kilometers above the ground. Ground-based observatories in the auroral zones operate networks of all-sky cameras, wide-angle instruments that image the entire hemisphere of sky simultaneously, recording the aurora's large-scale structure and how it evolves over time. These cameras run automatically through the polar night, building archives of auroral activity that span decades and allow researchers to study long-term patterns, seasonal variations, and the relationship between auroral behavior and the solar cycle. Magnetometers placed across the northern hemisphere at high latitudes measure the fluctuations in Earth's magnetic field produced by the ionospheric currents driving the aurora, providing a complementary dataset that can be compared with the optical observations to build a more complete picture of what is happening. Incoherent scatter radars, powerful radar systems operating in the auroral zones, probe the ionosphere directly, measuring the density and temperature and velocity of the electrons and ions at auroral altitudes. These instruments can track how the ionosphere responds during a substorm, how the particle precipitation changes the electrical properties of the upper atmosphere, and how long the effects persist after the storm has passed. The radars at Tromsø in Norway, at Sondrestrom in Greenland, at Poker Flat in Alaska, have been producing data for decades, long enough that the datasets they have built are irreplaceable resources for understanding the aurora's behavior across different phases of the solar cycle. Rockets have been an important tool as well. Sounding rockets, small, unguided research rockets designed to carry instruments to specific altitudes and return data during their brief flight, can be launched directly into an active aurora, measuring in situ the particle fluxes, electric fields, and plasma properties that ground-based instruments can only infer indirectly. A rocket passing through an auroral arc for 30 seconds of direct measurement provides a kind of data that no remote sensing can replicate. Norway's Andøya Space Center and Alaska's Poker Flat Research Range have been launching sounding rockets into auroras for decades, each mission adding to the detailed picture of what is physically happening inside the lights. Satellites, naturally, have transformed aurora science. Missions like the Defense Meteorological Satellite Program, the DMSP satellites, have produced long records of auroral imagery from orbit. The IMAGE mission mapped the global structure of the aurora and the magnetosphere simultaneously. The FAST satellite, Fast Auroral Snapshot, flew directly through the auroral acceleration region and measured, with extraordinary precision, the electric fields and particle populations responsible for accelerating electrons into the atmosphere. The Cluster mission, a constellation of 4 spacecraft flying in formation through the magnetosphere, allowed researchers to distinguish spatial structures from temporal variations in a way that a single spacecraft cannot. More recently, the swarm satellites and various small satellite constellations have continued building the observational record. But perhaps one of the more unexpected contributors to aurora science in recent years has been ordinary people. Citizen science programs, organized efforts to harness the observational capacity of non-professional skywatchers, have produced genuine scientific discoveries in the aurora field. The most striking example is a phenomenon called STEVE, which stands for Strong Thermal Emission Velocity Enhancement. STEVE appears as a narrow, ribbon-like arc of mauve or white light, often accompanied by a picket fence pattern of green vertical stripes, occurring at latitudes equatorward of the typical auroral zone. It was documented extensively by aurora photographers in Canada and elsewhere, initially because it was unusual and beautiful. When researchers began to study the photographs systematically, they realized that STEVE was not simply an unusual aurora. It was something distinct, produced by a different mechanism than the typical particle precipitation aurora, associated with a fast-moving stream of hot plasma in the subauroral ionosphere. STEVE had almost certainly been seen before, but it had never been formally documented, never studied, never named, because there had never previously been a large community of dedicated aurora photographers producing nightly imagery from the right latitudes. The citizen scientists found something that the professional science community had missed, not because they had better instruments, but because they had more eyes in more places, systematically photographing the sky on every clear night. The relationship between citizen observation and professional science in aurora research is genuinely productive. Amateur astronomers contribute observations, particularly of unusual forms and events at lower latitudes. Photographers building up libraries of aurora images over years of dedicated watching have contributed to studies of auroral morphology, the shapes and structures the aurora takes, in ways that supplement the automated camera networks. And the growing community of people who care enough about the aurora to learn its patterns, to invest in equipment, to travel to see it, creates a distributed observing network that no government agency could afford to replicate. The International Space Station has given us yet another perspective, one that was simply unavailable before humans began living continuously in low Earth orbit. The station orbits at roughly 400 kilometers altitude, which places it within the aurora on many occasions. Astronauts looking out the windows or cupola of the station have photographed and described the aurora from the inside, looking down at the curtains of light from above, seeing the structure of the display from a vantage point that reveals the horizontal extent and internal organization of the oval in ways that ground-based observation cannot. Images taken from the station showing the aurora curving away along the limb of the Earth, with the dark ocean below and the stars above, are among the most striking photographs that space exploration has produced. From the station, the aurora does not look like curtains. It looks like a luminous band, a glowing ring around the pole, sometimes narrow and structured, sometimes broad and diffuse, always organized by the invisible geometry of the magnetic field. Astronauts have described watching substorms unfold from above, watching the oval suddenly brighten and expand, watching rays shoot poleward across the sky below them as the magnetosphere releases a burst of energy. From inside, it is less dramatic than from the ground, no sense of the movement and depth that gives the aurora its impact from below, but it offers a clarity of scale and structure that is scientifically invaluable and aesthetically remarkable in its own way. Now, a question worth sitting with: is the aurora unique to Earth? It is not. Not even close. Aurora-like phenomena occur wherever the right conditions exist, a planet with a magnetic field, or even without one, exposed to energetic particle bombardment. The solar system turns out to be full of them. Jupiter has auroras, and by any measure, they are the most spectacular in the solar system. Jupiter's magnetic field is roughly 20,000 times stronger than Earth's, and it extends millions of kilometers into space, a magnetosphere so large that, if it were visible from Earth, it would appear larger than the full moon in our sky. The auroras this produces are correspondingly enormous. They form a continuous, glowing oval around each of Jupiter's poles, not intermittent like Earth's, but persistent, driven by a combination of the solar wind and the rapid rotation of Jupiter's enormous magnetosphere. Jupiter's auroras are brightest not where the solar wind is strongest but where the magnetic field lines connect to its moon Io, a volcanically active world that pumps sulfur dioxide into the Jovian magnetosphere at a prodigious rate, providing a constant source of charged particles that the magnetic field funnels toward the planet's poles. Jupiter's aurora is, in a sense, powered in part by a moon. The relationship between Io and Jupiter produces a footprint, a distinct bright spot in the auroral oval that traces the magnetic connection between the two bodies. Saturn has auroras, similarly organized around its magnetic poles, similarly driven by the combined input of the solar wind and the influence of its moons. The Cassini spacecraft, which orbited Saturn for 13 years before its mission ended in 2017, produced detailed observations of Saturn's auroras at ultraviolet wavelengths, showing a dynamic, evolving oval that responded to solar wind conditions in ways both similar to and different from Earth's. Uranus and Neptune, the ice giants, both have magnetic fields, unusual ones, tilted significantly from their rotation axes, producing magnetospheres with complex, asymmetric geometries. Both are expected to have auroras, though they have been observed only distantly and incompletely. Even moons have auroras. Jupiter's moon Ganymede, the largest moon in the solar system and the only moon known to have its own magnetic field, has auroras produced by the interaction of its magnetic field with the surrounding Jovian magnetosphere. These Ganymede auroras were observed by the Hubble Space Telescope, their presence deduced from ultraviolet observations. And then there is Mars. Mars has no global magnetic field. It lost that long ago, as its core cooled and the dynamo that generated it shut down. Without a global field, you might expect Mars to have no aurora at all. But Mars does have aurora, of a distinctly unusual kind. Remnant patches of magnetized crust, distributed unevenly across the Martian surface, create local magnetic anomalies, small, patchy fields that extend a short distance above the surface. Where energetic particles from the solar wind encounter these localized fields, they are guided downward, producing aurora above specific regions of the Martian surface. These Martian auroras are patchy, geographically anchored, and quite different in character from the organized oval aurora of Earth. But they are real, and they have been observed by spacecraft orbiting Mars. The aurora, in all these forms, is not an earthly novelty. It is a fundamental feature of how magnetized planets interact with stellar winds. Wherever you have a star producing a flow of charged particles, and a planet or moon with a magnetic field to interact with it, you are likely to find the aurora in some form. It is one of the most universal phenomena in planetary science. And here, in the quiet of the ending, it is worth pausing for a moment on what all of this means. The sun is always active. Even at solar minimum, even on the quietest days of the solar cycle, the solar wind is flowing outward, the magnetosphere is responding, electrons are precipitating into the polar atmosphere, and the aurora is glowing, faintly, perhaps, barely detectable, but present. The connection between the sun and Earth is never zero. It is never switched off. The flow of energy between them is constant, varying in intensity but never stopping, a continuous exchange across 150 million kilometers of space. The northern lights are the most visible expression of this relationship. They are the place where the connection becomes apparent, where something happening 93 million miles away becomes something you can see with the naked eye, from the surface of the Earth, on a cold clear night in the far north. Everything else about the aurora, the physics, the colors, the sounds, the myths, the disruptions it causes, the instruments we use to study it, all of it flows from this single underlying fact. The sun and the earth are in a constant relationship. They have been since the earth formed, 4.5 billion years ago. They will be for as long as the sun continues to burn. We live on the inside of that relationship. We are surrounded by it, embedded in it, affected by it in ways we are still working to fully understand. The magnetosphere that protects us from the solar wind is itself shaped by the solar wind. The atmosphere that sustains us is, at its highest reaches, constantly being touched, heated, ionized, and illuminated by the sun's continuous outpouring of energy and matter. The aurora is where all of that becomes visible. A luminous seam between the sun's reach and Earth's shelter. A curtain made of physics and light, hanging in the dark above the poles, moving and breathing and changing, never the same twice, never entirely predictable, never quite finished. On the clearest nights, in the darkest places, When the solar wind is right and the magnetosphere is singing, it fills the sky from horizon to horizon, and for a few hours it is possible to feel, without quite being able to explain it, that you are seeing something true about the universe. Not a spectacle arranged for your benefit. Not a performance with a beginning and an end. Just the universe, doing what it does, vast and indifferent and incidentally, breathtakingly beautiful. The lights were there before we arrived. They will be there long after we are gone. And tonight, somewhere above the Arctic, they are there now,